Welcome back. Let's go ahead and go through the example that I posed to you at the end of the last segment. To restate it, we have this infectious individual. Note that person A may be asymptomatic, but the key is that they're contagious. Remaining in room for 30 minutes, obviously breathing, with no ventilation in the room. And she or he is not coughing. The room is 5,000 cubic feet in volume, floor area 700 square feet, maintained at 50% relative humidity. We'll assume that all the coarse aerosol deposits on the table, that's 8 foot by 4 foot, 32 square feet in area. Person B enters 1 hour after person A departs, stays in the room for 15 minutes and does not use a mask, touching the table once, then touching fingers to nose. And we want to compute the total exposure from the fomite and from inhalation. So our approach is first to calculate the total emission from person A in fine and coarse aerosols. The fine aerosols diluting with the air, the coarse aerosols depositing on the surface. Then what is the decay in 1 hour intervening between the time that person A leaves and the time that person B comes in, both in the air and on the surface? For inhalation, how much is breathed and what might be the retention in the respiratory tract? For fomites, what's the transference from surface to finger and from finger to nose? So for emission, if we assume that the influenza data, is typical of SARS-CoV-2, and we use the data from slide 10 of the first part of this week's class, we expect with the 30-minute release, 5,000 RNA copies in the fine aerosol, 10,000 RNA copies in the coarse aerosol. But we don't know what proportion is infectious. So what's the ratio of RNA to viable virus? Or as a reciprocal, the relationship between viable virus to RNA. We assume, I'll assume for this calculation, 0.1. But there's a fairly broad range for this number, depending on the virus and probably depending upon the intermediate conditions in which the virus has experienced from release to uptake by a second person. And there are ranges from RNA viruses for anywhere in, let's say, 1 in 10,000 to 1 in 10. Applying this ratio, we have 50 viruses in the fine aerosol, 100 viruses released to the room in the coarse aerosol. Now the concentration in the exposed media for the fine aerosol, we assume completely mixed with room volume. 5,000 cubic feet gives us 0.01 viruses per cubic foot. On the surface, assuming that all the viruses will deposit to the table, we get 3 viruses per square foot. Now we consider decay. And this is from slide 16 of the first segment of this week's lecture. In air, based on the actual measurements with SARS-CoV-2, a half-life of 1 hour, meaning a decay rate of 0.69 per hour. If we apply the exponential relationship, this gives us a remaining concentration in the air of 0.005 viruses per cubic foot. On surface, a somewhat longer half-life, 5.5 hours, a somewhat smaller decay rate. So the 3 viruses per cubic foot, excuse me, this should be per square foot, goes down to 2.6 viruses per square foot after the 1 hour contact. Now for the fomite exposure, so we start out with the number on the previous slide. From slide 19, a transference from surface to fingertips of 0.3. From slide 18, a transference from fingerprint to nose of 0.34. We need to know the area of a finger. Let's use about 1 square inch, or dividing by 144 to get consistent units, 0.0069 square feet. So we multiply the surface concentration remaining by the 2 transference factors, by the area of the fingertip, and this tells us that the amount transferred to the nose is 0.0018 infectious virus. For inhalation, our air concentration, 0.005 per cubic foot. We need to know the breathing rate. This is a typical number for adults. Moderate activity. It varies by activity. It varies somewhat by gender. An overall range, 5 to 8 liters per minute. We'll use 7, which translate into cubic feet per hour, 2.1 cubic feet per hour. From slide 14, we'll select a retention of 0.3. So we multiply the concentration times the breathing rate times 15 minutes in the room times retention gives us 0.0008 viruses deposited. So what can we observe and conclude from this? The first is inhalation exposure cannot be ignored, certainly compared to the fomite exposure. Now we've excluded direct deposition of larger particles onto person B. We could work out a scenario of that as well, although in this case, person B is not in the room contemporaneously with person A, so there is no opportunity for direct contact. Now, these doses of organisms are fractional. right? If we go back, for inhalation exposure, 0.0008. For fomites, 0.0018. What does that mean? We can't have a fraction of a living organism. So what that means is maybe in the case of inhalation exposure, if we had 1,000 people going through the same scenario, on average, somewhat less than one person would be exposed to a viable virus. In the case of fomites, if we had 1,000 people being exposed, on average between 1 and 2 would be exposed to a viable virus. For those of you that have had some statistics, think of this as the Poisson mean. And then from a Poisson distribution, you could calculate the number of individuals with 0, the proportion of individuals with 0, 1, 2, etc., viruses being exposed. What does that mean in terms of risk? Well, we'll defer this to a future lecture, but if you remember back to our overall risk paradigm, we've calculated the exposure. We now need to couple that with dose response. And from that, we get an overall estimate of risk. Clearly, this is a very, very simplified problem. We've assumed all deposition occurs on the table. That's certainly oversimplified. We assume air is completely mixed with no makeup ventilation. That's obviously oversimplified. You'd have a stagnant, stale room. Next week, we'll talk about how we consider ventilation in the context of indoor air quality and inhalation exposure. And we might also think about how we could incorporate non-medical interventions. What would happen if person A would wear a mask? What would happen and/or if person B would wear a mask? Of what type? How much risk reduction would we have? What data would we need to assess that? What would happen if we decontaminated the surface of that table between occupancy? Maybe use a cleaning or a disinfectant that achieved some amount of reduction on the table before contact. Or perhaps if person B, after they touch the table, wash their hands quickly before having the opportunity to touch their nose or mouth. Or what would happen if after person A left, we did a total room decontamination, not just for the surface, but for the indoor air? How much reduction of risk could we achieve? So now we have linkages between the release of the virus and potential non-medical interventions that we might do as engineers. So with that, that ends our lecture today. Have a good week. Remember, the discussion problem is posted, and I'll see you on the screen next week.